Can start? Okay. So today we are going to do the last part, I hope, of chapter 4 about linear algebra revisited by heaps of pieces. So the first two parts, we have done McMahon master theorem, which I consider to be included in classical linear algebra. We have done matrix inversion. We have done Jacobi identity, log of determinant equal plus, etc. We have seen Kelly-Hamilton. And today, the last identity is Jacobi duality. All this using the three basic lemmas about heaps of pieces. So I recall you the classical theorem of Jacobi duality in linear algebra. So you take two subsets of the integer 1 to k. I did not write there, but I and j are subset of the segment 1 to k. I take a k by k matrix. And then Jacobi identity told you that you take this matrix 1 minus a, the inverse of this matrix. This means you take the minor with the row indexed by I and column indexed by j, and you take the determinant. And then this equal to something like a cofactor, something, so it's a determinant of the matrix itself. Here it was the inverse matrix. Now I have the matrix itself, and here it's j bar and I bar as a complementary of I and j inside the segment 1 to k. And you have to divide by the determinant. So it's related to see the minor of a matrix to the minor of the inverse matrix. Instead of it taking a matrix B, I can take a matrix 1 minus A as soon as A is 1 minus B. So it's the same. So instead of proving this, I have a better theorem, which I call the main theorem. The main theorem says that if I take the left-hand side of Jacobi identity, I have the following interpretation. The left-hand side of it, so the minor of this matrix is equal to the sum over all permutation. This is a symmetric group with L element, minus 1, the number of inversion of the permutation. And here you have a sum. So you have a blue path, eta 1, eta 2, eta L. So this path, eta 1 go from I1 to sigma of I1, etc. Eta L go from IL to sigma of IL. These paths are self-avoiding paths. And here you have the weight of a heap. You have a heaps of cycle. And there is a condition that the maximal piece of the heap must intersect one of the paths eta. And it's not finished. I have a super condition that the paths eta are pairwise disjoint. So you see, I have this. We know that 1 minus this matrix, if I take the term ij, so this means I reduce I to one element, j to one element. The term ij of this matrix is the sum of the weight of all the paths going from I to j if I have a certain weight of the path. Usually the weight will be going from I to j. I will take the formal variable a index ij if a index ij is the ij element of the matrix A. So at least one, maybe 2, 3, 4, intersect one of the paths.
What is L?
What is M?
L is the
L is the cardinality of I and j. Here, I forget to put, I take a k by k matrix, so I take the segment 1k, the matrix has k row, k column. I take a subset of L element, I and j, two subset, which is going to be the indices of the row, the indices of the column. I take the minor corresponding to this indices of row and column. Jacobi identity give you this, but I think I have a better, more beautiful theorem, which keep, yes?
Does the index ij mean you delete those rows and those columns? Ith columns or add?
No, I take them. The minor, we have a square matrix, k by k matrix. Any minor is defined by you take some row, I, you take some row J, column J, and you take the submatrix, square matrix, L by L. Of course, when I take the complementary in the Jacobi identity, then I am deleting the row in column I and J, and I am taking the complementary.
It's also called the complementary.
The complement?
This theorem is also called the complementary minor theorem.
Complementary man?
Jacobi's
Complement.
complementary
Yes.
minor.
Yes, yes. So it's different name.
Sigma is a bijection from
Sigma is a permutation.
Oh, not a bijection.
No,
So
permutation.
I is I1 to I.
It's a permutation on L element. L is the size of I and J. And so take a minor, so it's a submatrix, and I take a permutation on L element. So I have a plus or minus, and then I take L blue paths. I take L self-avoiding paths, which are pairwise disjoint. They are 2 by 2 disjoint.
Sigma J1.
So maybe it should be
Sigma J1 to J.
No, so sigma J, see J sub sigma.
Sigma of A1. Sigma is a permutation from 1 to L to the segment 1 to L. So if I have A1, I1 in I, then I am going to sigma of I1, which will be an element of J. It's a permutation.
So it should be J sub sigma 1.
I,
Should be J.
or sigma should be a bijection.
oh, no, bijection. Oh, yes, no. Okay, it's confusing because I and J are not the same. So it's a bijection, yes. Sorry, it's a bijection from I to J. And I can reduce to a permutation this and have an inversion number.
So there is no. Yeah, there is a.
So it's something like if there is only one element in I and J, this means in fact I have only one path, a self-avoiding path, and below there is a heaps of cycle, which maximum piece must intersect theta. So this was exactly the bijection between path and a pair, a self-avoiding path, and a heaps of cycle. So I have an extension of this bijection. See, when you have many paths, so there is a plus or minus. There is it's not totally positive, and then you remain the fact that all the blue paths are all self-avoiding and 2 by 2 disjoint, and below there is a beautiful heaps of cycle E, which such that the maximal piece of this heaps must intersect at least one of the blue paths. Maybe several blue paths are intersected by the same cycle. So this is the main theorem I will prove today. The consequence of this main theorem is Jacobi identity. Yes? Question?
Goes over E, right?
Just,
The etas and E.
sorry,
This is very confusing. So your sum should run over all the etas as well as over heaps E, right?
The sum is over E also.
yes. E, yes, sub over E, yes. Oop. Okay, E is a heaps of, yes, sub over all possible heaps.
All possible.
So this E should be here, yes. Under the summation, the summation sign, E, usually we put everything below, but I put this here to have some place to put my I'm supposed to be on the corner of this screen. So sometimes I have problem to put everything and remain this corner empty. So now from this main theorem, in fact, you can deduce Jacobi identity, Jacobi duality. So just apply the inversion lemma, n over d, because you have a heaps of cycle with some condition on the maximal piece. The projection of a maximal piece must intersect this blue path. So we know that the denominator is a trivial heaps of cycle, which means the determinant of 1 minus a. So we have already seen this many times. Trivial heaps of cycle is this. It's given by determinant of 1 minus a. Now the numerator is going to be, what is the numerator? It's going to be this. So you have your blue path. The numerator you have, for a given, it's the sum over all this configuration of blue paths with the weight, self-avoiding all pairwise disjoint. And then I put some cycle which are disjoint, all cycles are disjoint from all the blue paths. This is the numerator. By applying the general inversion lemma, it's trivial heaps of cycle, which must not intersect, does not belong to what we call before capital M, so they must not intersect the blue paths. So you have a summation of all blue paths, and once you fix the configuration of blue paths, in the picture maybe they don't intersect here, you see. When means they intersect, means they have a common vertex, a black point, must be somewhere. Here they don't intersect. So they are 2 by 2 disjoint, they are self-avoiding walk, and then you have to put some cycle in green on the possible position where there is no collision with the blue path. Let's see the special case to well understand what happens. Special case where there is reduced to one element. So the left-hand side is the sum of the weight of all the paths going from I to j, and the right, by the bijection between paths and pair self-avoiding one and the heaps of cycle. So if I fix the self-avoiding walk, I am a numerator divided by a determinant, and this is what we have done several times, at least twice, that the sum of the weight of all the paths going from I to j is this cofactor. It was Nij was, you give a blue path, like a self-avoiding path going from I to j, you put some cycle 2 by 2 disjoint in the blue path. The sum of all this with -1, always it's alternating generating function of trivial heaps. So this is the numerator, this is the denominator, and this is the classical inversion formula for matrix. You have to see that the numerator is a cofactor, it's a minor of the inverse matrix. Why? It's because we have seen already this. If I take the cofactor ji of this matrix, then it's related to deleting the row I, the row j in the column I. You put a 1 here, and if you take the determinant of this, it's up to the sign, it's exactly the minor, the cofactor. So putting a 1 here, if I take this determinant, then because of the general interpretation that determinant of 1 minus the matrix is the sum of the weight of all the trivial heaps of cycle, so here it means I have a cycle now here. And these red edges mean I am forcing an edge between j and I. This means I am putting a 1 here. So taking this determinant give you this picture of trivial heaps of cycle, 2 by 2 disjoint, and if you delete the red edges, then you get back the previous configuration with a single blue path and some cycle. Okay? General case. So now I have, for any starting set I and x at j, then I have the same denominator, the determinant, so trivial heaps of cycle, and the numerator, it's going to be, by the general inversion formula, it's you fix the blue path, and then you have all the cycle 2 by 2 disjoint from the blue path. Everybody is pairwise disjoint, but there is still this bijection between the set I and set j with a number of inversion. So this would be the numerator, and the lemma that this numerator equal to this. This is exercise in linear algebra, but it goes beyond the topics of this class because everything must be bijective, and this is just a line of calculus. So to give you an idea of the proof, it's you have this picture, you have this numerator, and I want to show that it's a determinant. Sorry.
What is S? S of I.
S of I is the sum of all the index I and the sum of all the index j. Oh, sorry, I forget to define this. So I and j are some indices, I1, I2, I3. I take the sum of all the indices I, which is S of I, and the sum of all the indices j, which is S of j. And then you see, you do the analog reasoning that when there was only one element, one column, one row deleted. So you take a matrix, taking a minor of the complementary matrix, a minor of j. This is the complement of j. This is the complement of I. So taking the minor, this is the blue part. If you collect them all the blue part, you get a matrix, a determinant. You get this determinant. But this determinant, this minor, is going to be related to this big determinant when I replace, I put a 1 in each of this. Here I have 4 elements in I, 4 elements j bar. So I put any permutation in this, 1, 1, 1. So this is going to be the permutation here, which appear with a sign. if you put a 1 everywhere, then taking the determinant of this means you are going to force some edges. And forcing the edges is the red edges. Like this. So you are making cycle. You see the blue path, you go back with the force edges red. This make a cycle. And the total, so total figure, it's a trivial ellipse of cycle, which give you this, this numerator. So you fill the... Then you have a question of the sign. You have to check this is linear algebra. You have a few calculus to check that this the plus and minus are the good sign when I go from this determinant or to the minor when I delete this column and row. So believe me, it's up to the sign. There is a few consideration of the sign to do, but this is a general idea that taking the numerator is taking this determinant, which means the ones are forcing the blue path to come back. So I have only cycle, the green cycle, and cycle from by a blue self-avoiding path plus the return edges in red. So this cycle are 2 by 2 disjoint. And again, it's you see, you go back to the classical theorem. The determinant of 1 minus a matrix is the sum of the weight of all the paths, the cycle 2 by 2 disjoint, trivial ellipse of cycle. So this is the idea, yes?
So you take permutation on n letters, right?
Yes, it's permutation.
But I bar and j bar are of size k minus n.
That actually should be I and J.
Those are I and j.
Ah, yes, I'm sorry, there's been I prepared just yesterday's morning the lecture, there's some mistake. So this would be I and J, okay. Yes, sorry, take off the bar. So there is some correction to do. Please note so that I can correct the slide. Give me the list of correction for, but video you cannot correct the mistake. That's the pleasure of video. Yes, try some comments. Yes, there is a website I will. The comments. Yes, yes. Oh, it's not a very serious error. I hope there is no. So I get this from the main, what I call the main theorem. I get this Jacobi duality theorem. Example. An example like this. So you have a 2 by 2, you see you have a graph with a certain number of vertices, 1, 2, 3, 4, 5, 6, 7, with 8 vertices. So the adjacent matrix is 8 by 8. And then I take the sub matrix where I is 1 and 2. I start from V1 and V2 here, and J is 3 and 4. And the 2 by 2 matrix is given by this. See, if I take a path, for example, going from V1 to V3, then this is a unique path, but you can make some cycle in this graph. So this unique path, which is A, B, D, F, H. So this is a numerator, and then making a lot of cycle, it explains the denominator here. Another path is this one, A, B, C. And then again, when you are here, on this path, you can put many cycles, which gives you this. GH corresponds to this path. See, the denominator corresponds to this cycle in red. Now the determinant is going to be this. You have to check because what you have to do, you have to put, by the main theorem, determinant, you have to put 2 self-avoiding walk, one going from 1 to 4, one going to from 2 to 3. So this is the 2 blue paths. And then you have to put a heaps of cycle below, which intersect one of the blue paths. So the heaps of cycle, it's only one cycle, and it's a pile of cycle, the same cycle, which appear here. 1 over 1 minus BDE. And A, B, C, G, H is a product of the weight of these 2 blue paths. Special case number 2.
And this comes with a minus sign because...
Because the permutation is exchanging...
3 and 2 to 4.
Yes, 1 go to 4 and go to 3. And because the matrix was 1, 2, 3, 4, the order, so the minus because of the transposition.
And there is no path which goes from 1 to 3 and 2 to 4.
From 1 to 3? No, there is one. We have seen.
No, simultaneously.
Ah, yes, no. If you have going from 1 to 3, then it's impossible to go from 2 to 4.
Right.
So the only configuration of blue paths, there is only one. From 2 to 4 is impossible, yes.
For any.
Yes, it's... So this example comes from a paper of Talaska in 2002. I will quote some... Special case number 2, a cyclic graph. Suppose there is no cycle. No.
Or directed
Acyclic is directed. No cycle means it can be if you take paths on a square lattice going to the northeast, you can go east or north. Then you can all these paths cannot go back. There is no cycle, but it's not a tree. It's a lattice. Take the square lattice, end by end, and then go east or north. Then you can get. So this term is cancelled. So what remains is only the pairwise blue path. And then we are exactly in the case of the class last year, chapter 5a, the so-called LGV lemma. Which means that taking a determinant is more or less taking non-intersecting paths. So the slides following come from the class last year. I have no time to adjust the notation. So sorry, the notation are the notation of last year. So maybe it's going to collide with notation, but I just extract a few slides of this class last year. So a path is 0 in the set of vertices S. Notation will go from S. So I have a weight of the path. You know what is the weight of the path, the product of the weight of the elementary step. And then I take the weighted path like this, and then you fix some point, starting point A1, A2, AK. You fix the ending point B1, B2, BK, and then I am taking the path for I and J, I am taking all the paths going from AI to BJ. So I take a matrix. This gives me a matrix. The term ij, it's a k by k matrix. The term ij is the sum of the weight of all the paths going from AI to bj. I suppose this sum is finite, especially if there is no cycle. There's a finite number of paths. And then, so if I write the definition of determinant is up to -1 number of inversion of the permutation. So sigma is a permutation on k element, and multiply by the weight of k paths, omega 1, omega 2, omega k, and each path omega I go from ai to b index sigma I. Just application of the definition of a determinant and definition of the matrix aij, the sum of the weight of all the paths. So the picture below this summation is this. Here the starting point, the ending point, and many paths which can intersect or don't intersect. So the classical LGV lemma, it's a special case. It's a special case when there is a crossing condition, especially when the walk are on the planar lattice and you don't go too far, you don't jump, you go to the next neighbor, and usually this condition is satisfied. So the crossing condition means that if you have any integer I less than j, so the starting point are totally ordered, ending point are totally ordered, and if you have any path starting from ai and j, and then omega, any path omega with a non-zero weight which go to bj prime, a path aj going to be I prime with I prime less than j prime. So you see, it seems they are interlacing, they are crossing. The order of the starting point is the reverse of the order of the ending point. And then the crossing condition means that these two paths must intersect somewhere. As soon as we have two paths like this, two index ij, two index I prime j prime, and two paths omega and eta, they must have a common vertex. This is a crossing condition. Then the LGV lemma in that case tell you that the determinant is equal to this. It's a sum over all paths omega 1, omega k. The paths omega I go from ai to bi, which means that the permutation is identity permutation, and the paths are 2 by 2 disjoint. So you see, when I take this big summation, the definition of the determinant is the sum of all this configuration, sum of all factorial n permutation. And in fact, you can have a lot of terms have the same weight, and they are going to cancel 2 by 2. We are going to have involution, which kills the term 2 by 2. And what remains is only the term related to the identity permutation. So on the n factorial permutation, there is a big dramatic cancellation. And even among the terms with the identity permutation, the paths are non-crossing. So you get this, you see. This is a general term of determinant. Taking the determinant is doing this. So if you want to eliminate cross in the path, if determinant was not existing, you should invent the determinant to be able to count non-crossing configuration of paths. So a very simple example. Take this determinant. Sometimes it's called the Fermat matrix. The term ij is I plus j choose I. You put the binomial or Pingala triangle coefficient, you put them like this. Now in normal Pascal, it's called Fermat, now, this matrix. I don't know if Pingala was putting his coefficient like this, it should be again Pingala matrix. But put the coefficient like this, you see, and the term ij of the matrix is nothing but the number of paths. So you have the square lattice, number of paths starting from I, ending term in j, and the elementary step are you go east or north to the next number. So of course, such path is just a binomial coefficient. The paths are length I plus j, and the path is given by sequence of north or east step, and you have just to choose the binomial coefficient to choose I north step and j east step, and then we get the number of paths. So the determinant is going to be the number of non-crossing configuration, because you can feel that the crossing condition is satisfied. So the determinant is this equal 1. So it's a one slide proof that this determinant is 1, because you have this unique configuration of non-crossing paths. Another example which has been very used many times in different topics, the binomial determinant. This will be my second example. Take a strictly increasing sequence of numbers, and this is an extension of the binomial coefficient. AI choose bj is a binomial coefficient, but if you take the determinant of this k by k matrix, so which I denoted like this, in the case k equal 1, you get back the binomial coefficient. So this determinant is a minor. Here is a Pingala triangle, and I suppose there is some 0 above the diagonal. So here is the coefficient here in this triangle, 70, is the number of paths going from AI equal 8 to bj equal 4. So the coefficient ij of my matrix is exactly the number of paths going from AI to bj with east and north step. So my determinant in this case, for example, if I take starting point 2, 3, 5, 8. So this is a minor, I am taking the minor of this matrix with the row 2, 3, 5, 8, and column 1, 2, 4, 6. So I have a 4 by 4 matrix. The crossing condition is satisfied. And then, so I claim that the binomial determinant like this is exactly the number of configuration of non-intersecting paths going from AI to omega I, go from AI to bj. With AI, it's a blue point on the vertical line, and bj the point on the diagonal. For example, this 4 by 4 minor of the Pascal triangle, it was a number of such configuration. So you have this number of configuration is a minor of this Pingala or Pascal triangle, and the immediate corollary, this minor, is a positive. So this is a proof that any minor or any determinant of binomial coefficient is a positive number. And sometimes it's 0. And you can immediately prove that the non-zero minor, if you take the k first row in column, is a Catalan number. So this theorem, binomial coefficient, have been used many times. You can reprove from this the formula, Hook-Lens formula for Young tableau. You can reprove also this famous formula of McMahon for plane partition. You see, when you have a plane partition like this, it's it's a heap. It's a heap of cubes, but there is no dependency relation. The only constraint is that the surface are decreasing. Such a plane partition, I go fast, but just an example, it's encoded by path, and this path can be transformed into binomial path, binomial determinant, and then by some lemma I explained last year, I go fast, but all this is explained in the class last year. We prove this formula, another formula of McMahon. We have seen the McMaster theorem and McMahon theorem. So this is some example, and now I will go more or less rapid to give a proof of the LGV lemma. So it's really inspiring to get the proof of the main theorem of the beginning. Let's prove it. So we have two special cases. One special case was I and j reduced to one element. this was the inversion matrix formula, and this was the bijection between path and self-avoided and the heaps of cycle. Now I have a second special case where there is no cycle, and then the general proof will try to extend both proofs to give the general proof. But it's inspiring to get carefully how we prove the LGB lemma. So we are going again to have a killing involution. So the configuration is you have a certain permutation. Now, so I go back now to n by n matrix. Sorry. No, this should be Sk. And there is k paths, omega 1, omega 2, omega k. Omega I go from AI to B sigma I, so the permutation on Sk to k by k matrix. And I take the configuration of non-crossing configuration. And I'm going to define an involution on the set of configuration which are crossing. I am going to define involution such that you see this configuration is going to be transformed into another one, and then the sign will change, but the weight will be invariant. So the total weight of all the paths, which is total weight product of all the weightages, will be invariant, but then there will be a change in the permutation, the sign will change, and the two terms associated in the involution will be killed 2 by 2. And what will remain is a term I cannot define the involution. It will be exactly this NC, the non-crossing configuration. So idea of the proof, you see, you have two paths. Suppose they intersect. Then if I take a common vertex like this, I can change this like this. See, this path takes this part, so I just exchange the two paths once they cross this point, and this is going to give me a new permutation, which of the sign will be minus the sign of the previous one, and the weight will be invariant. So the idea is very simple. You have to switch two paths. The sign is changed, but the weight is invariant. So the problem is, well, we have to define a certain point, a certain pair of paths, a point, so that if you repeat the process, you go back to the original configuration. So you have to precisely define the point P. It's a very different way. So suppose two paths, there is some intersection between the paths. So first you take the smallest I, such that omega I has an intersection with another path. So you see I have omega 1, omega 2, no path is crossing, but omega I there is a path intersecting with this one. Now you take the choice you take the first point on the path where there is some other path coming. Maybe there is several paths coming. so you take the smallest j. The blue points are totally ordered. So you take the smallest intake j such that this path is going to intersect on this point. So once you have done this, okay, I do the switch, and you can easily say that if you repeat the switch, it go back to the origin. So this gives you involution killing the term 2 by 2, and the involution is not defined on the non-crossing configuration, and that's the end of the proof. In the case of the crossing condition, if I don't have the crossing condition, I can do exactly the same, but maybe some term, plus and minus term remain. So the general form of LGB lemma is you have a summation determinant of Ij, exactly the same. You have a summation of all non-intersecting configuration, but maybe some permutation is remaining with a plus or minus, and the permutation, the paths are such that AI go to B index sigma I. And they are not intersecting. So this can be useful also to have this general term. And what we are doing with the main theorem, we have this general term with an inversion number of the permutation. So proof of the main theorem. So I just repeat you the main theorem. So you have to prove that the determinant, the minor for the matrix 1 minus A inverse with the column rho I and column J is this big summation over blue path, the heaps of cycle with the condition of the maximal piece, and the path must be 2 by 2 disjoint. So first I can write the definition of my determinant. It's a summation of with permutation and with sum of all the weight of all the paths. And then the idea is to use, if you have, I am a good student, I follow everything Professor Viennot gave, and I use the bijection. Okay, I am going to give the tool of the class. The path is in fact in bijection with a pair eta I ei. So I replace each path by, there is a self-avoiding walk in blue, and there is a product of many, each index, there is a heaps. I just replace, you see, for each path, omega I have a bijection with a pair eta I ei. And I put all this product of weight. So I have product of the blue path, product of all the heap, with the condition that now in each heap ei, the maximal piece must intersect eta I. It's individual. There is a product. Each heap is correspond to a blue path. So if I apply this bijection for example, the first heap, E1, the path omega give me this, the path omega 2 give me this, omega 3 give me this, omega 4 give me this. Now I have to put everything together, which give me this. But how to do? All the cycles are going to collide. It's just a Cartesian product of each heap, each path. I have to put all this. So you see the path, the cycle, each heaps correspond to one of the blue paths. Here I have 4 heaps of different color. Each heaps correspond to one of these blue paths on the top, but I don't know how to put them together. It's that's a big problem. It's so this picture I can write like this. So this is just interpretation of my determinant of the left-hand side of the main theorem, and the right-hand side of the main theorem tell you that this big summation, which is here with some different heaps of different colors related to some different blue paths, the main theorem tell you that this is equal to this. That now the blue paths are non-intersecting, and the heap, there is only one heap. There is E. So there is only one heap with the condition that the maximal pieces of the heap E must intersect the blue path. So that's a big problem. Is it possible? You see, what we have to do is we have this big messy picture, which came from the interpretation and using the bijection key. I have a product of heaps and blue paths. How to go from this? They may intersect, the blue paths are self-avoiding, but they may intersect. How to delete this intersection? Now they don't intersect. And instead of having a mixing of many heaps, I have only one heap. So how to handle this big mess of paths, heaps, etc. So I try to put some direct bijection. I don't succeed. It's maybe one idea is coming from physics, but I cannot manage it. You see, when there is one path, there's a loop erasing process, the cycles are falling down. So why not to do the loop erasing process simultaneously on all the paths at the same time, and each time you choose one of the edges of the path, see the paths are growing one by one. So you are going to put some label, so that maybe, okay, it's your turn, you go one edges. So the path, you have to choose which path is going to go first, and maybe one cycle will fall down. So the cycle will fall down from the different paths. So with this labeling, compatible with the order in each path, I get a heaps of cycle, satisfying the condition of my main theorem. But the problem is how to go back, because I have a label heaps of cycle with some constraint. So this should be, there is 2 physicists, very bright physicists in this room, so they should manage when you have when you have a random path which goes simultaneously, how can I handle this to be able to go back once I have my heaps? It would be a loop erasing process, simultaneous loop erasing process in different paths, but because you have to know which cycle fall before, so you choose the order which path, and it's just a multinomial coefficient. If n the total number of edges of all the paths, you have a multinomial coefficient, the number of ways to label the path so that you know in which order they are going to go forth, in which order the cycle are going to fall down. So you are mixing all the cycle of all the paths. So it's feel that I am going close to the right number of my denotator, but I did not succeed. I work hard, but this is why there is some mistake in the slide. Also, I can try to, okay, maybe it was a wrong idea, I can go back to the past. And maybe try to do the involution the same as the LGV lemma where there was no cycle. Maybe try to do the involution here, directly on the path without considering the cycle and the self-folding walk. So the problem is the following. Now there is a very serious problem because we are taking the first time, etc., but take the path omega 1. The first time is crossing omega 2 is here. But if you take omega 2, the first time it's crossing omega 1 is here. So to define my pivot point where I'm going to switch the path, there is a main problem. And this main problem was solved by Lalonde in his Mémoire de maîtrise, in his thesis. He solved this problem by giving an killing involution directly on the path. But this is very technical, complicated. Here it was more very complicated. Here it's less complicated. But it's too technical, so I have decided not to give you this proof. But there exists an involution. Maybe open problem, try to find a better involution. Not know if you can improve. But there is a nice way to prove this theorem is to use the paper of Fomin. In 2001, he was working on the loop erasing and the positivity related to positivity in the Grassmannian. So here is Fomin theorem. So we are using again this bijection, but you use only the loop erasing part. We don't use the heap. So it's a proof between considering only the path or considering the pair, the path plus the heaps. We consider only the loop erase, what remains when you do the bijection key. Only eta, the blue path. So eta I call this LE of omega I. It's a loop erase. This is very well known. A loop erase random walk. We have seen this in when I show you Wilson algorithm to write a random spanning tree on a graph. And so the Fomin theorem tells you that this summation is equal to this summation. So what is the difference? You see here is exactly the same. Omega 1, omega L go from I1 to sigma 1, IL to sigma L, etc. You have still the -1 inversion, but now there is a condition on this path which involves the loop erase part of each part. So the condition is the following. For every index I and j between 1 and L, with I less than j, then the loop erase part of omega I, so the blue path eta I, is disjoint from omega j. So it's a condition mixing. On one part there is a path, omega j. All the paths before, I am considering all the paths before the loop erase part, the blue path, and I look with the other paths, which not considering the blue part, and the condition is this. You see, it's a beautiful condition. And so now, so you have destroyed the symmetry of the main theorem tells you that, okay, it's a heaps of cycle, so that the maximal path must intersect all my blue paths. So it's totally symmetric. But here now we lost the symmetry. It's amazing that this is still a symmetric condition. We lost the symmetry, but we gain a beautiful involution. So the involution is the following. I do it for two paths. And then, with the idea of the LGV lemma, where going from 2 to any path, it's easy to do. So let's do it for only two paths. So I have two paths, omega 1, omega 2. The first path in red, in green, sorry. I have omega 1 in green, and the loop erase path part of omega 1 is in blue. So say you have your green path, and when you do the loop erase process, what you get is the blue path, self-avoiding walk. Now I take omega 2, any path, going from I2 to sigma of I2, omega 2. And if they intersect, I am going to do the involution by switching the paths. If they intersect, then if omega 2 intersect eta 1, be careful. The second path, I suppose, intersect the loop erase part, the blue path. So if omega 2 intersect eta 1, the blue path, let V be the first intersection point following the path omega 1 from I1. On the blue path, I should say, you have the green path, and you look on this blue part. The first time you are going to find a vertex which belongs to omega 2. All this portion, you see in the picture, the purple path does not appear. The first time that the path, the omega 2, intersect, so the first time following the omega 1. Because omega 2 can intersect many times the red point here. So you have to be careful. You have to think this as a heaps of edges, as a flow. See, if you think as a flow, it's better to understand the involution. So I take V, the first intersection of omega 2 and omega 1, when I follow the path omega 1. So this defines me a factorization, V. So if V, this red point, is I1, then omega prime 1 is empty. If not, let UV, the unique edge on the path theta, ending in V. Which means, you see, when the path, on the blue path, there is an edge which goes to this V. There is an edge UV here. And this edge is on the blue path. In terms of flow, if you think in terms of flow, it's a maximal edge. And you cut the path, the green path omega 1, following the path, when the path goes through this maximal edges. Because the path can go many times in certain edges, but this edges is the maximal for the flow. When you are on the blue path, the loop erase walk, nobody will come on these edges anymore. So you cut the path, the green path. When is the path? It's a sequence of edges. It can be many times the same edges, but when the path goes through these edges here, on the blue part, then you cut omega here. In terms of flow, you see, this edges is maximal in the flow, and you cut the path the last time the path goes through these edges of the flow. And then I'm going to cut the purple path in two parts also, and such as that V does not belong to omega prime 2. This means that you cut omega 2 the first time you visit the vertex V. You have your purple path. The first time you visit V, then you cut it. And then you do the involution by switching the two paths. Exercise, well, you have to, it's not so, you have really to think how it works. This is an involution. If you repeat the process, so you have to do now what is the loop erase path of the purple path. Therefore, you have to really think. If you think in relief, in space with the flow, then you will think have a good intuition of what happened. In fact, in the Fomin paper, Fomin is explaining in his paper all this. In fact, the characterization of V is given by condition 1 and 2. The characterization where I cut the green path, it's the last entry in the edge sequence which contribute to this, and the second part of where I cut of the green path does not visit any vertex of this. So it's technical, but these two conditions is a characterization of where I cut the path green path. You flip the two paths, you do the involution, and you have to show that now the same characterization remain, and you can go back, flip again by using this characterization of where you cut the green path. So see, it's not trivial, this, and then so I go, leave you as an exercise to think about it. It's a little technical, but it's a scene reversing involution. And so what we have done for two paths, you can extend it for three paths by inspiring from the idea of the case where there is no cycle and LGV And that's the end of the proof of Fomin theorem.
So this was Fomin's own proof?
Yes. So Fomin, he proved, what he proved, he proved Fomin theorem, which is this. So Fomin theorem is that the sum of the weight of all these paths is equal to this. And this, we know it's come from the minor, it's come from the determinant of 1 minus I minus 1, indexed by I and j. So this is the left-hand side of Jacobi identity, and this gives you this. And he stopped here. It's amazing that this is not symmetric, but it's symmetric, but it's not trivial to say that it's symmetric in the family of paths. So that was the Fomin contribution. But at that time, there was no, the main theorem give you, there is a heaps behind of cycle independently of all the paths. So second part now of my this lecture is to go to now the proof of the main theorem, which proves that the Fomin identity, in fact, is symmetric in the set of paths. So proof. Now we are going to prove with using completely the bijection with the heaps of cycle. And the main theorem is this following. You have the sum of the weight of all the blue paths 2 by 2 disjoint and the weight of single heap of cycle. So how to go to a single heap of cycle? So I am going to prove that this equal to this. We know from Fomin theorem that this is the determinant, the left-hand half of Jacobi. I am going to prove that this equal to this. And this now is easy. Using the power of heaps. So this is the picture which gives you the right-hand side of the main theorem. This contribution there. All the blue paths, all the heaps. The blue paths are 2 by 2 disjoint. The heaps is such that the maximal piece must intersect one of the blue paths. So this is the picture. And I have to go now to this picture, must give me the Fomin interpretation. With the loop arrays with this condition where I is less than j, then all the paths, the green paths omega j, doesn't intersect the loop array path of the omega I. So now the proof is easy because again you have to use one of our favorite operators, the push operator. Suppose you have this set of blue paths and then I can define a second. Suppose take omega 1 and eta 1. Consider this as a solid pieces. Now consider this as a cycle and self-avoiding path are the basic piece of new heaps of pieces. So it means that we have a heaps of cycle, and then the maximal piece of my heaps of cycle and self-avoiding walk is only self-avoiding walk on the top. Suppose the walk are completely solid, and then I can push. You see, take eta 1 and push, take the path and press down. A lot of cycle is going to be embarked in the process. Exactly, we have done this many, many times for the logarithmic lemma, etc. Take the whole path and push it down. So what you get is this. Now what remains, you push again down. You push, push, push. So you get a sequence of such a thing. The previous heaps E is a product of E1, E2, E3. Because I push, E1 is going out of the heap, is going down, then E2, then E3. Now for each of these sequences, I have some paths by the reverse bijection. So what is the picture? First, I push the first blue path. A certain heaps of cycle is going to be embarked in this pushing. Then I push the second. Then I push the third. I push the fourth. So you have a sequence of pair blue path and heaps of cycle. And this sequence, you see easily it satisfies the Fomin condition. If you take this path, for example, the third path, the path corresponding to this is not intersecting any of these blue paths. Because if it was intersecting somewhere, it would have been embarked in the process of pushing down. And because the blue paths are 2 by 2 disjoint. When I push all this down, the first push, then the second push, in this, if I go back to the path related to this path does not intersect the blue path here and here. It cannot, the blue part cannot intersect this, and if it was intersecting, a cycle of this would intersect here, but because of the pushing process, all cycle which cycle here would have been embarked in the process. If you think of this process, it's easy to see that any path corresponding to this pair does not intersect any of the blue paths. So this is the Fermi condition, and this is the end of the proof, and this is the end of the proof of the main theorem.
Here, in fact, WI intersection WJ is empty, right? Because
Who is empty?
It could have been in some other part of the thing, it could have been passing, right? All you know is eta 1, eta 2. So it can still go over the same thing. So you already pushed.
He's saying WI, omega I intersect omega J is itself.
Omega, the intersection. Yes, it can intersect. Omega I and omega J can intersect. Because your path, which is here, why they can intersect?
then if there is some cycle which is there, that would have already been pushed down.
Because this cycle here, for example, maybe can be above this cycle. You see, this cycle here. Suppose this cycle here can be above this one, and when you push, it stays above. See, you have the whole. So one of the Brown cycle here can be remain and intersect this path. You can. Or this one is hidden. See, this cycle should be here. This cycle should be here, which is above this cycle. So this cycle is remain in the pushing process. What I claim is they cannot intersect the blue part. Because if they intersect the blue part, then they will be embarked in the process. You can tell me, okay, but the blue part can intersect this blue part. No, the blue part does not intersect. So this is the main condition. The blue path doesn't intersect. And then if some cycle of the path remain here, it is above. This is a kind of pyramid. This is a kind of pyramid with a unique maximal piece is a self-avoiding walk. And all the below, they all cycle. Say with a unique pyramid like this. But then there must be, the pyramid is here. There may be some cycle. You can push, and some cycle remain from the other path. So they can intersect omega I, omega J. But the clever condition is they don't intersect. One path does not intersect the loop erase part of the other. And this is a dissymmetric condition. And now, by using heaps of pieces, all this is, then we have give back the symmetric condition, which is the main theorem. You just have a heaps of cycle, a single heaps of cycle, which is bounded above by all my blue paths. And so this gives me the Jacobi identity, its proof. So there is other proof in physics. The physicist Tanasa and his physicist in our cometal group in Bordeaux, and he gave a proof using Grassmann algebra integral. So this comes from physics. Maybe some people would say, okay, this is much simpler proof than the bijective involution proof, which seems to be complicated. It's to your own taste. I like bijection, involution, and if you prefer Grassmann algebra, then you go to this paper. So there is also another way to prove this identity. Another way should be to write like this. And then make a killing involution on this pair. So this is another way to prove it. But you lose the main theorem with the heaps of cycle, and I think this is the main part of the Jacobi identity is a consequence of this, but the main theorem is to have these heaps of cycle and the blue path above. So we have seen a particular case of this proof. It's you remember there was the inversion proof like this. If you go back to the proof of the inversion lemma, there is an involution. I multiply d by this, and then I make my transfer set. But there is even a simpler proof, which was given in the course last year, a direct proof, completely direct. When you have the path, you have the determinant, you have two things on the left-hand side. You have a path multiplied by the determinant, so you have a path in blue, a configuration of cycle 2 by 2 disjoint, and then maybe you are going, if the path intersect itself, you will cut the cycle and put it to the configuration of cycle, or maybe if you have a configuration of cycle, you can integrate the cycle in the path, so you see you can move the cycle from the path or move the cycle configuration, and there is a direct involution. I gave this last year, so it's possible to do this idea with many paths, and this idea also have been done by Lalonde and by Talaska, and but Talaska, you have to combine this simple idea for I and j or one element with the idea of switching the path. So if you combine both ideas, switch the path or incorporate a cycle in a path, so this is another proof when you write the identity like this. So there is a positivity. All this picture come from some consideration of positivity in Grassmannian. This is some complement. Or this is an active subject, and also there is some connection with Mayer expansion in physics, loop ensemble. So all this story of paths, you see, but the basic, if you look at carefully at many papers, the basis can come from this basic lemma on heaps. And for example, you will see in the class about graph theory, we will see many times that there is some zeta function, for example, and there is some geometric function. You have to prove this. So after a long computation, people use the Jacobi identity, exponentielle, the trace, the log, etc. So many different papers or consideration. You have to go back some classical theorem of linear algebra. But this Jacobi identity comes from the logarithmic lemma. And if you look carefully, the problem people are handling, it can be proved directly with the logarithmic lemma in heaps. So in fact, this is the source, the root of many different things, even the root of problem in linear algebra. So you don't need linear algebra. You can go directly to the root, which give you at the same time linear algebra or some theorem. We will see the zeta function in the next chapter on graph theory. So if you have the crossing condition, for the general theorem now with the crossing condition. So general theorem is a crossing condition. Now it's in this case, there is no more inversion. So crossing condition is sigma is the identity, and then you have a sum over all blue paths and a sum over a single heap with no more identity, no more permutation. Which means that if the weights are positive, everybody is positive. So there are a lot of, this was a question of Fomin, that the positivity in Grassmannian, positivity is because the minor, you have a lot of minor matrices, and they are interpreted by this object, a pair of paths, family of paths, and with the heap. So in the case of crossing condition, you see you have this picture. That you have a heaps of cycle, a unique heaps of cycle, and the maximal piece must intersect the blue path, and all the blue paths are 2 by 2 disjoint, and permutation is identity. I1 go to J1, I2 go to J2, I3 go to J3, etc. So I will conclude. Oh, I went fast. I will conclude with a funny theorem. Suppose you take the square lattice, and so the matrix, adjacency matrix of the square lattice from 0 to k, it's k plus 1 to the square times k plus 1 to the square. There is k plus 1 to the square. I take the adjacency matrix of the square lattice, and I take I, the minor, I start all these points 0k, and j, all these points 1 to 0 to k. So the term ij of this minor is the sum of the paths, all the paths going from I to j, from this to this, where the path can go to the next neighbor north, east, west, or south. And
So then you can cycle.
they can make cycle, yeah. Good, we are in a general theorem where we make cycle. I try to use this general theorem. I don't know if because it's not well known. In fact, the general theorem was done by Lalonde in 1990, long time ago. It's with non-crossing paths floating on the heaps of cycle, and non-crossing paths floating on the top of the heap. So we should do something. Physicists should do something with this. Instead of applying Jacobi duality, etc. No, because there is the main theorem is above the Jacobi identity, to my opinion. So you see, the generating function of parts going from I to j, it's an infinite generating function. But I put some weight, you can make probability or anything you want. So I have a generating function from all this to this. So the term ij is the sum of this inverse matrix, the sum of the weight of all the paths going from I to j, and then the determinant indexed by the row I and the column j is a minor with k plus 1 row, k plus 1 column in this big, huge matrix. And so what is it? Applying the general theorem exercise. Apply the general theorem. So you have a heaps of cycle, and above you have a configuration of non-crossing blue path, 2 by 2 disjoint. The crossing condition is satisfied. So the numerator is this. It's a unique configuration of a Pingala-Fermat-Pascal matrices, which is the weight of this divided by determinant of 1 minus a. So up to a constant, it's the inverse of determinant, which is heaps of cycle. Because any heaps of cycle are going to have intersection with this very close net of paths. So make something, physicist, can you apply this to something? Or this idea, you see, to have a determinant? Because now, what is this determinant? It's going to be 2 by 2 disjoint loops cycle inside the grid lattice, so we are close to some other problem in statistical mechanics. So
But then this denominator doesn't have a simple formula, right?
no, yes, it's the inverse of this determinant. No, there is no formula for this one. Determinant, it's
If I put
all disjoint cycle on a grid. You know, there is no formula. It's a very
yeah, but if I want to, I can't put all weights equal to 1, then I
Yes.
get infinity.
yes.
So if you put some weights, then
Good weight and
good weight, maybe all
Maybe-
x or vertical
Yes.
y or something. Can one compute this?
I don't know. But then you have also this path here. If you start from 0, if you are in the infinite lattice, start from 0 and go back to 0. Then such path, in fact, is what we call the shuffle of 2 Dick words. Because if you look only the east or west step, you have a Dick path going east or west, x bar. So going only east or west, this makes horizontally a Dick path. Going north or south, you have another Dick path. So any path starting from 0 going back to 0 is just a sequence of x bar, y bar, where restricted to x bar give you a Dick path, restricted to y bar give you another Dick path. So it's what we call the shuffle. Shuffle means all the possible interlacing of two Dick paths. And we know that, so this is a sum of all binomial coefficients, n choose 2k, ck, c Catalan, etc. And there is a very nice proof that, in fact, this is equal to cn times cn plus 1. The number of such paths of length 2n is a product of 2 Catalan numbers. And there is a nice bijective proof using a Baxter permutation. We have seen this last year. So there is nice, these paths have a nice bijection. So I don't know, the path starting from I to j would be the shuffle of left factor and right factor of 2 Dick paths. So there is some, maybe some formula for the generating function of such paths. But in the infinite lattice, now we are bounding the lattice on a square. Well, it's just for fun. I give you this just to have an application of the main theorem, but there should be more application when you have some.
So just sorry.
Yes.
To understand. So on the infinite lattice, what will it be? It will be all possible paths starting and ending on
At 0,
0.
this is equal the number of such paths to Catalan number index n multiply Catalan number n plus 1.
No, on the infinite lattice.
On the infinite lattice, yes.
No,
Number of paths of length 2n.
of length 2n.
Yes, of given length is a product of 2 Catalan.
Okay.
Naturally, it's a shuffle of 2 Dick paths, but this shuffle is going to be in bijection, is a product of 2 Catalans. Bijection is not obvious at all.
No, it's not.
So there is some nice combinatorics. It's related to what is called Baxter permutation. We have seen Baxter permutation last year also. So sorry for the students who were not last year, but this is some complementary just to finish as a fireworks of this main theorem. So I think we have finished the chapter of linear algebra with this, and next time, so we will start graph theory revisited with the heaps of pieces. The next chapter, acyclic orientation, chromatic polynomial, etc., etc. So thank you very much.